So we are in the middle of the Arctic, and our plane, the LC-130, is just taking off without us. I'm sure you're judging my Kim Kardashian fit.
Oh no, you're good, man. It looks warm.
It was the cheapest one we could get. This episode of Insane Engineering is a little bit different from the other episodes because we're here in the middle of the Arctic and the plane we're going to be talking about is right behind me. It's the LC-130. It's a rocket-assisted takeoff plane with skis, weird as shit, and we're about to take off in it with rockets, and I'm very excited. The LC-130 is designed specifically to operate in one of the harshest environments possible, the freezing polar regions of our planet. Here, the LC-130 supports research bases in both the Arctic and the Antarctic, and I, somehow, managed to convince the 109th Airlift Wing to fly me to the Arctic with them. Which meant I got to experience one of the coolest takeoffs of any plane, because this variant of the C-130 not only has skis equipped to land on snow, but can be fitted with 8 rocket pods to help it get off the ground in the worst conditions imaginable. After landing in a remote ice core drilling site to resupply their scientists, we were forced to quickly take off again as temperatures were 40 degrees below zero, and sticking around on the ground too long could cause issues for the plane. But as we started bouncing on mounds of snow, it became obvious that we had overshot the skiway. With the skis plowing through the snow, the pilots were struggling to get up to speed and get that front ski off the ground. And then this happened. Fucking light them. This is the insane engineering of the LC-130. I can't understate how badass these rocket pods, known as JATO bottles, are. The Blue Angels C-130 sometimes uses them in air shows, and it's a spectacular sight every time, but they weren't created to show off. These rocket pods were developed to allow planes to take off from shorter runways with heavier loads. At one point, the US military even experimented with launching F-84 Thunderjets from the back of a trailer with one huge rocket pod. The most audacious plan to utilize JATO had to be Operation Credible Sport. The US military was planning to use rockets to land and take off from this stadium in Iran during the Iranian hostage crisis in 1980. Located just across the street from the US Embassy, it was the perfect location to quickly extract the hostages. Lockheed had planned to use 58 of these bottles on a C-130, with sets pointing forward to slow down the plane, another set facing down to decrease the descent rate, and finally another set in the more familiar rearward-facing direction to provide a boost on takeoff. The sudden braking and upwards thrust from the rockets on landing would require the plane's structure to be strengthened. On this occasion, the initial rocket pods firing above the cockpit supposedly blinded the pilots, who, in confusion, ignited the second set of forward-facing rockets. This reduced the plane's forward velocity to near zero, and without the downward-facing rockets firing, the plane plummeted down onto the runway, causing the wing to buckle and break. Another airframe was ready, but the plan was never used as the hostages were released with help from Algerian diplomacy. While our mission may not have been as daring, personally, I think it was vastly cooler. We flew from Kangerlussuaq, a small town surrounding the largest airport in Greenland. This is where the 109th and the National Science Foundation based their Arctic operations from. From here, we flew into East Grip, an ice core drilling site that sits on top of 3 kilometers of ice. The mission for the day was to drop off researchers and resupply the base. Our time on the ground was extremely tight. We had all of 30 minutes on the ground before we needed to get back on the plane and take off. Supplies were even dropped out of the rear cargo door as we were slowing down on the skiway to save time. While we were running around outside filming as much as we could, the flight engineers were attaching the rocket pods to the attachment points below and behind the wings. Each of the rocket pods had 3 attachment points for this purpose. Once attached, they screw in the igniter into the JATO bottle here. The igniter uses a pretty old-school method of ignition. The initial charge is black powder, which is ignited by an electrical charge when the pilot hits a button in the cockpit. This black powder charge then ignites pellets made from aluminium and potassium perchlorate. The propellant itself is made from a metal polymethacrylate binder with a potassium perchlorate oxidizer. Once ignited, this charge rapidly raises the surface temperature of the internal solid propellant to ignition temperature, while increasing the internal pressure to ensure stable combustion. The inner cavity of the rocket motor is circular, which means the thrust increases over time. This is because the cavity walls are increasing in surface area, and thus more propellant is burning and contributing to thrust. Each motor produces around 67 kilonewton-seconds of maximum impulse. Impulse is simply force over time. This is the impulse graph for these exact rocket motors. And we can find the total impulse by calculating the area under this graph. If the rockets lasted longer or produced more force, the impulse would be higher. When we took off from Iskrip, these rockets were actually developing much less force, but lasted longer. This was because the outside temperature was -40 degrees. That's so cold that it's the same temperature in both Fahrenheit and Celsius. I was actually told to get back into the plane while I was outside filming because my face was showing the first signs of frostbite. Temperature affects solid rocket motors because lower temperatures means it takes more time and energy to get the propellant to ignition temperature, meaning the propellant burns slower and develops less thrust, but over a longer time. This is what the impulse graph at 16 degrees Celsius looks like, and this is what it looks like at -60. The overall impulse is lower for the lower temperature propellants as some energy is wasted in heating up the propellant, but in the grand scheme of things it's pretty negligible, as the energy released is much higher than the energy needed to heat up the propellant. These days, the JATO bottles are rarely used. We weren't even sure if we were going to get to experience an assisted takeoff on this trip. On every other expedition during our week with the 109th, we managed to get off the ground with just engine power. But at Iskrip, something was different. I spoke with the chief pilot of the 109th, Nate Dickinson, to learn more about how pilots decide to use the assisted takeoff.
Do you have a decision speed? Say when we were taking off from Iskrip, I think we actually overran the skiway and we were out in like just fresh snow.
Yeah, we call it going long, yep.
Yeah, and I was talking to the pilot after takeoff then of what was the decision point there, what was your thinking on when we actually fired the JATO bottles. And he was saying like we just got up to 70 knots, we were struggling to get above it, we needed an extra bit of speed and he fired them. But at that point we were off the skiway.
Yes.
And obviously in a normal takeoff, you have your decision speeds on like when to abort it. Do you have similar things here?
We do. It depends a lot on our gross weight, but also our center of gravity, what we call, you hear pilots talking about CG. And we, as pilots on the snow, prefer an aft, a rearward center of gravity. So we do everything we can. Our load masters are critical on this. On any cargo we get, trying to configure it so that we have a very aft CG. It allows us the most authority with the elevator for getting off the skiway and allows us to accelerate as quick as we can. So that's what we always aim for. But there are times when, due to the way the cargo is or how much fuel you have on board, you can't give yourself the most favorable conditions. And that those make for days where pilots really earn their pay. So they got to work hard, or you don't get off the skiway. There's days. I was in McMurdo this year. We've got a nice long skiway, and we did 4 attempted slides and still couldn't get out of there. And it wasn't a day to go skiing,
And that's all just the resistance on the snow?
Exactly, yeah, because our skis are actually Teflon coated. They've got skags on them, so they're set up very similar to downhill skis or Nordic skis. But the way the snow was, we had a snowstorm that had rolled in the day before and put just a fresh, 2-3 inches of snow on the skiway, and it really, really slows us down. So a lot of times when the pilots are just walking out to the ramp or to the plane, they'll be assessing the snow right as we're walking out there, seeing how deep we're sinking into it, if it's sticking to our boots, just looking at it that way. So it's kind of an important part of ski flying.
And is there any other differences between the LC-130 and the regular C-130 in terms of do you have special high lift devices or different procedures for takeoff other than the JATO bottles?
The flight controls are no different. Our hydraulic system is modified to account for the very large actuators that are in the skis. So all the hydraulics for the skis are actually built into the skis. So the hydraulic system's modified. Those are really the biggest differences on it. They had to move some other systems around, but they're still all the same systems as another, slick C-130. But flight controls are all the same. Our authority on the flight controls is the same. So, they paint our birds a little bit different, and they put some different non-skid paint on some of the upper surfaces so that when maintainers are up there working, they have got a little bit more to step on. So it's not so slick, but just because of the environmental concerns. But yeah, other than that, the ski system is really a really big hydraulic modification, and then just the fairings and the skis themselves. So yeah.
The skis needed additional hydraulic power as they require additional actuation with extra hydraulics. The LC-130 can land on normal runways with the landing gear wheels peeking through the skis. But when the skis are needed, they are pushed further down and rotated underneath the wheels. We saw this in action on the snow in the Arctic. After landing, the skis are usually raised to prevent them from getting frozen to the ground. When it's time to take off, the hydraulics push the skis down, lifting the entire plane up and rotate backwards so the skis are cushioned by the plane's landing gear. The skis are designed to allow the plane to slide across the top of the snow as much as possible. They are designed in a fairly similar way to traditional sports skis. The quickest way to tell what kind of snow a pair of skis are designed for is by looking at the width of the ski. If a skier is sticking to groomed slopes, they will want a thinner ski, but going off-piste into deeper ungroomed snow will require a wider ski to allow the skier to stay on top of the snow. The skiways the LC-130 land on are partially groomed, but keep in mind they are usually being serviced by a small group of researchers with limited machinery. The LC-130 has fairly wide skis and frequently has to deal with completely ungroomed snow. This means there are a lot of variables that a pilot has to consider, particularly on takeoff. The snow depth, how wet or hard the snow is, and the texture of the mounds and troughs of the snow. All of these factors affect how these skis will interact with the snow, and the skis create a lot of surface friction that slows the plane down and makes taking off all the more difficult. When taking off from a traditional runway, pilots often use a flight computer to determine some parameters for takeoff. Data on altitude, runway length, temperature, and aircraft weight are all factored in, and the flight computer will give the pilot the optimum flap angle. For the uninitiated, the flap is a high-lift device used for slow-speed flight. You will frequently see them fully extended for landings on commercial flights, particularly on shorter runways, as they allow the wings to generate more lift at a slower speed. This reduces the braking distance upon landing. One of the really unique things about the LC-130 are the procedures around flap percentage on takeoff. Because there are so many unknown variables as a result of the ski's interaction with the snow, the pilots can't always determine an optimum flap angle. I asked the 109th chief pilot about these procedures.
I was talking to the pilot again after takeoff, and he was saying there's some unique, just even takeoff procedures that you're able to vary the flap angle, which
So
isn't
that's
typical.
One thing we do that's very different is we typically will start our takeoff slides or our attempts for takeoff the way any C-130 does, which is at 50% flaps. And we assess the skiway that way. And most of the time we're able to get airborne at 50% flaps. But there's times when we can't, either due to our CG, due to our gross weight, snow conditions, whatever it is. And then we train to where our flight engineers, under our instruction, can move the flaps. And there's a whole bunch of different techniques, from starting at no flaps to eventually rolling 50, starting at 100% flaps, rolling back to 50. Most of the pilots, our goal is to get to the end of the skiway and have the flaps back at 50%, so it's as close to a normal takeoff attitude and trim as possible. But there are times when ski pilots have to get airborne at 100% flaps, which is a pretty critical situation. You're really slow, and the limitations on our aircraft are kind of different when we're that slow. So,
Can you talk about the trade-offs of that? It's speed versus lift, right?
Yeah, it is speed versus lift. And the problem is when we get as slow as doing like 100% flap takeoff, your ailerons are your limiting flight control surface. And you can get yourself in what we call an engine out situation, where your critical engine goes out and you don't have enough aileron authority to right the plane and keep it under your control, and you're essentially along for the ride. And the only way to fix that is pull back power on that other asymmetrical engine that's good, and essentially you're 2-engine takeoff at that stage of the game, and you'll be setting the plane down straight ahead. And we train for that. We try to never, using 100% flap for takeoff would be one of the last tricks we'd use to try to get out of there. But we talk about it, we brief it, we practice it. We practice it in the simulator all the time. But yeah, it's pretty wild. We just the other day we were on the Raven ramp and trying to get out of there, and we had to use 100% flaps just to get ourselves off the ramp. And it was just that extra lift was able to just lighten up the main skis enough that we could pull out of there because the ramp was pretty soft. So there's a lot of seat of your pants that you got to do in this business. So yeah.
An LC-130 pilot taking off from the Antarctic in 1971 had the mother of all nightmare engine out scenarios. This LC-130 was taking off from the D-59 field camp after a successful resupply. However, as the plane's skis left the ground, disaster struck. 2 JATO bottles broke free of their attachment points and flew loose. With the worst luck imaginable, one of them flew directly up the tailpipe of the number 2 engine, while the other struck the propeller. The debris from the number 2 propeller then took out the number 1 engine. The plane was now airborne with no power available on the left wing and full power on the right. As Chief Pilot Nate Dickinson stated, the only course of action in a scenario like this is to throttle the functioning engines back and try to set the plane back down. However, with this level of asymmetric thrust, the LC-130 began to yaw hard left, and its right wing rose rapidly. Pilot Ed Gabriel somehow managed to get the plane level before impact and saved the 10 people on board and earned himself the Air Medal. The crew had to live in Arctic survival shelters for 3 days until they could be rescued. This LC-130 was stranded in the Antarctic for 16 years, gradually being buried up to its vertical stabilizer in snow. But after 3 years of planning, it was uncovered and repaired enough to be flown home in 1988. The cause of the JATO bottle detachment was eventually found and corrected for. A company that had been hired to refurbish the plane had painted over the mounting hinges for the JATO bottles, and the buildup of paint in that location had prevented them from locking into place. Approximately 256,000 of these motors were produced by Aerojet. But these rocket pods have actually been out of production for quite some time. And here's the crazy thing, the Air Force is actually running out of them. Rocket-assisted takeoffs were something that were incredibly useful for these older C-130s. You may notice that this 1970s era LC-130 is a little different from the one we flew. It only had 4 blades on its propeller. Today, thanks to high-performance propellers with modern turboprop engines, the LC-130 rarely needs these rocket pods to get off the ground. The LC-130 once flew with 4 bladed propellers and later upgraded to 6 But the latest variants of the C-130 are equipped with state-of-the-art NP2000 8-bladed composite propellers from Collins Aerospace. Choosing the number of blades for a propeller is a little counterintuitive. Propeller blades are basically just wings that are rotating in a circle to produce lift. Wings generate more lift with more wing area, and the same applies for propellers. Increasing the diameter was not an option for two reasons. The first is ground clearance. The C-130 is designed to operate from rough airfields, where debris could damage the propellers, so we want them as high off the ground as possible. We also want to keep the tips of the propeller blades below 0.9 Mach. Increasing the length of the blade increases the tip speed, as these engines are constant speed. So, the diameter of the propellers could not change. We can, however, play around with the area of the blades in other ways, either by increasing the chord length of a single blade or by increasing the number of blades. Both will increase the power drawn from the engine. As engines have become more powerful, we've seen propellers get wider and more numerous. One of the weirdest examples of this is the Douglas A2D Skyshark, a fighter plane with a monstrously powerful turboprop engine. As the propellers couldn't increase in length due to ground clearance issues, the engineers used contra-rotating propellers with blades with disproportionately large chord lengths. The engines of the LC-130 have not been upgraded between the switch from the old 4-bladed propeller and the new 8-bladed propeller. The power being drawn is the same. They have instead traded chord length for more propellers. The increased performance primarily comes from a change in materials. These composite blades are about half the weight of the aluminium blades that came before them, and carbon fiber composites are much stiffer than aluminium. This freed the designers to optimize the aerofoil design for the LC-130's needs. On takeoff, these propellers generate about 20% more thrust, which has shortened fully laden takeoffs by about 300 meters. The brunt of this increased takeoff thrust comes from the aerofoil, which has been designed with rounder edges. These rounder aerofoils increase the stall angle, meaning the angle of attack on the propellers can be increased before airflow detaches from the surface of the blade. A higher angle of attack means more lift. This allows the propeller to generate more thrust on takeoff. The blades are then feathered to a lower angle of attack during cruise. Thanks to these propellers, these rocket-assisted takeoffs are largely a thing of the past, but something else that I had assumed had become obsolete thanks to newer technologies has actually remained. One of the first things I noticed while standing on the flight deck was the navigator's seat. It had one of those old-school radar screens, which honestly I had assumed had become obsolete for navigation with the advent of GPS. But as the plane's navigator, Major Jefferson Wood, told me, it's actually vital for the LC-130's navigation in the Arctic.
So could you talk me through what the navigation to somewhere like East Grip, what tools you're using, how you actually know where it is on the ice cap? Because obviously it looks, you're going out there, it's just white everywhere.
Right. Well, so the nice thing is we have this radar here, which, like I said, it's not on right now, but if it was on, when you're dealing with a barren surface like the ice cap, you know, all of a sudden you throw a couple of structures up on that and it lights that radar up very nicely. And also, when you have an established camp where they've built a skiway, they put those flags up, like I'm sure you've seen out at Raven there. So all the skiways are built to a similar standard, and those flags light the radar up very nicely as well. And so a full skiway like East Grip camp, when you're talking, you know, roughly 10,000 foot runway with flags along the side, either end of that skiway going out 3 miles, you have lead-in flags that they're basically made crosses that go all the way out 3 miles on either end, and those show up beautifully on the radar. So I can see those from 50 plus miles away.
And you're just using the radar dome in the plane?
Yeah, you're using the radar in the aircraft. So,
that's incredible.
Yeah, it's a pretty sensitive radar, and it does a very nice job of painting those targets. And so that really is, in terms of the basic day-to-day navigation, you probably don't need me. However, when you're in the weather trying to get into a camp like East Grip or a camp like Raven where the conditions are less than ideal, that's when it's nice to have somebody sitting here who's sole job is to have my face in the radar and literally telling the pilots, okay, turn to this heading, okay.
Yeah, when we flew out yesterday, the cloud cover was pretty low. I think it was like 200 meters or something, and it was even coming into land. It's like I can't tell if this is clouds or the actual ice cap.
Yep.
Yeah.
Yeah, and I think I was the navigator on that.
Really?
Yeah.
So what was that like for you?
So I'm monitoring that as well and making sure they're, if you don't want to be too high, especially when you're getting close, because you don't want to have to like dive down to land on the skiway. You really want kind of a steady rate of descent going in. So I'm kind of watching all of that because visually for the pilots, there's not a lot of visual cues out there. So they're really flying their instruments and listening to what I'm telling them as well.
Having a navigator in conditions like this is absolutely vital. There is no air traffic control in the Arctic after all. This whole trip was mind-blowing. We spent an entire week in Greenland with the 109th. We filmed their Arctic survival training. We filmed even more interviews with the crew of the planes, shot a behind-the-scenes discussion of the entire trip with Graham, our on-site production coordinator, and shot an entire tour of the town. None of this could be uploaded here, but it is on Nebula. Given the channel's name and what most people subscribe for, I try not to go on off-topic tangents. I feel the need to pack the video with as much detailed engineering information as possible and keep the video going with little eureka moments evenly scattered throughout the video to keep your attention. Because of that, I end up leaving a lot of really interesting information that I would love to share out of the video. You have already heard every talking point on why you should sign up to Nebula at this point. Lifetime subscriptions, incredibly cheap monthly subscriptions. It's a creator-owned streaming service. You click the link, you pay money, and you get extra content, which helps us make more content. You know the deal. So let me tell you a little bit more about Kangerlussuaq instead. And this little town is one of the weirdest places I've ever been in my life. The Jado bottles that the LC-130 uses are scattered all over the town, being recycled as cigarette bins. The only roads out of the place lead directly to the barren ice cap. Everything here has been shipped in to the local harbour when it's accessible in summer, or flown in. Much of that cargo is flown in on airliners that are both cargo and passenger planes, and this creates a problem. The town relies on this airport to survive in many ways, and that's all in jeopardy. The airport was recently transferred from US control to Danish, which itself brought a lot of change. But now the Greenland government is building a new airport in Nuuk, Greenland's capital, which will divert much of the traffic that could once only land here, putting the entire town's future into question. We were fascinated by this town. It's truly on the edge of the world, and one person in the town captured our imagination more than anyone, Chris Sorensen. Chris became a bit of an enigma to us during our stay. He was our landlord. He was tasked with escorting us around the Danish-owned military base. His name and contact information was plastered on warning messages in the cars we rented, telling us where in town was off-limit to tourists. And most bizarrely, one night, or day, it's hard to remember since it never got dark there, while we were in a local store getting beer for a night in with our new Air Force friends, there he was, behind the counter. I started comparing him to Nurse Joy from Pokemon because he seemed to work everywhere. We joked that we had 24 hours of sunlight because Chris needed them to complete all his jobs. We started calling him the King of the North, and on our last day there, we asked if we could interview him. During that interview, he drove us around the entire village, pointing things out and telling us his story, how he ended up here, how he worked his way up the ranks of this small town, buying businesses, being a reliable liaison, and falling in love with the tight-knit community. But that's all in jeopardy now. We have turned his story into our documentary, King of the North, that you can watch right now.